Alright, hi everyone. My name is HP, and today I'll be talking about some of the work that I've done on improving the motion correction of 70 fMRI time series using boundary-based registration. So firstly, some quick background on my task. It's a visual attention task where subjects are prompted to attend to two or four locations, and they are required to do a same different judgment. And we have two permutations where we can try and decode for attended location or attended category, but the specific details are not really necessary for this talk, since we'll mostly be covering very generic methods, a very generic method that should work on all fMRI time series. For our data, we have 6 participants, two of which they underwent 2 sessions at 3T, 2 sessions at 7T, and we have also 1 localizer session at 3T that we use to identify both early visual areas as well as higher visual areas. For the 7T data, this was 0.8 millimeter isotropic data, and it was a 2.39 second TR. We had a total of 8 runs per session, and each run lasted for approximately 11 minutes. And in terms of acquisition, because we are interested in both the early visual areas as well as the higher visual areas in both the dorsal and ventral stream, so we had relatively interesting acquisition orientation. So if the images later look slightly weird to you, it's because we are using this acquisition box. Right. So for our data, the first thing we did was slice time correction using SPM12, and following that we did top-up correction using FSL. So top-up is just calculating the phase distortion using the 5 reverse phase encode images that we acquired at the start of each run and the first 5 images of a time series. And we then apply this correction to all the data to remove any distortion due to phase. Following that, we need to realign the time series. And because we have 8 runs that we are trying to realign, so we have to do this for both within and across runs. So the first thing we tried was just using standard realignment using SPM12. So the SPM realign function that uses a sum of squares cost function. And if you look at this video, you can see that there is quite a bit of jittering of the brain still going on even after we do motion correction. And yeah, so obviously this, like, if we're interested in any voxel-based activations, this sort of realignment is not good enough for our purposes. So the next thing we tried, so moving on, I'll talk about what boundary-based registration is and how we can use it to improve the motion correction from what we've just seen. So boundary-based registration uses the gray matter boundaries. They have to first generate either using free surfer or FSL. And from personal experience, I found the free surfer boundaries to be much more accurate, so I've been using that. And what it does is that it aligns the EPI image such that the change of intensity in the EPI image is normal to the boundary. So kind of what this picture is illustrating. And this is a rigid 6 degree of freedom 6 degree of freedom transform, and it has shown good results for the co-registration of functional to structural data. But here we are doing something slightly different in that we are trying to register functional data to functional data across a time series. So how do we do that? So we take the raw images that have underwent slice time correction and top up, and we generate a mean image. And the first thing we do is apply a BBR to this mean image. Next, we split the entire time series into individual volumes, and for each volume we do a BBR to structural on it separately. So one thing that I didn't mention initially is that one drawback of this method is that it's very computationally expensive. So each volume, if you were to do a BBR to the structural, it takes approximately 5 to 6 minutes. So if you imagine you have an entire time series that's like 200 volumes, this will take a while. So one neat thing that I found that helps to speed up things a lot is that when you calculated the registration for the mean image, you can use that as your initial seed to start the BBR for each volume. And because you're already starting quite near the convergence point, this will speed up the function by quite a lot. So now each volume takes about 1 minute on average. And once you've done registering each volume to the structural, you can then recombine it into a time series And because each volume is realigned to the structural, so they are effectively realigned to each other. And all you need to do after that is to reslice each volume according to the first volume so that you have the same voxel registration. So, an added benefit that I didn't mention is that by doing this entire BBR realignment, your final volumes are already become directly registered to the structural. So it's much easier if you want to do further analysis with laminar layers, or if you want to do something like mapping the voxels into surface space. And so as an illustration of the differences, so this was the standard realignment that I showed earlier. So you can still see the brain jitters by quite a lot. And if you look at the BBR version, you can see that brain is basically stationary now. Right. Hopefully this is obvious enough. And of course, like looking at videos is one thing. The other thing is to try and come up with some quantitative metrics. So the first thing we looked at was TSNR of the entire time series. And you can see that when you use BBR registration realignment, you have much better TSNR for all 6 subjects. And on top of that, we wanted to look at where BBR provides the most benefits. So what I did was I took the TSNR map of the results using BBR and subtracted the standard TSNR map. So from this, you get a nice map where the red and yellow voxels are voxels where BBR has improved the TSNR significantly, and the blue voxels are voxels where the standard realignment methods work better. And you can see that BBR really helps a lot more in the surfaces, and this is kind of expected because we are driving this whole realignment using the boundaries. Right. And the next thing we looked at was the functional contrast to noise ratio. And so for the early visual areas, the contrast that we're using was a locational contrast, and for the higher visual areas, the contrast that we're using was a categorical contrast. And you can see that while the data is slightly noisier and there is definitely some variance there, in all the regions there's still somewhat of a benefit of BBR, and especially so in the early visual areas. And similarly, another measure that we could use was looking at the percentage variance explained by the GLM. So you expect that a less noisy data will have a higher percentage variance explained, and that is kind of what you see here with BBR again performing better than the standard realignment. So now the question becomes, like, why is BBR performing better? And so we thought of some of the differences between BBR and what SPM uses. So firstly, BBR uses a structural image. So what this means is that the structural image is acquired at has much more detail. So it could be that this higher detail level allows your realignment to be better. So one alternative that I tried subsequently was to use SPM co-register to the structural in place of BBR. So the entire pipeline that I showed you previously, you still do the same thing. So you do SPM co-registration for each volume to the structural and see whether this generates a better realignment. And another difference is that BBR is driven only by boundary information, whereas like what we've done in SPM uses the entire volume, so both voxels inside and outside the brain. So it could be that like the out of brain voxels that are messing up the SPM realignment. So another thing that we could try was using brain mass to remove out of brain voxels. And there's also been some other sites that have shown improved results if they use a much smaller brain mass. So because of that, I generated 2 masks that I wanted to try and run the data by. So firstly was the full brain mask, and this was just generated using the gray matter segmentation in FreeSurfer and registered to the functional data in BBR. And I just did a simple dilation and erosion just to make sure that all the sulci voxels are captured as well. And to generate the small mask, all I did was erode the full brain mask by 10 voxels. And so on the right hand side, you can kind of see what it looks like. And so now we have essentially 5 different methods: the BBR method that I've been using, the standard method, and applying 2 different masks, and using SPM co-register. And you can see that even though using the mask, I'm not sure whether it's very obvious, but using the mask provides a slight benefit compared to standard standard realignment, but BBR still performs better than all the other data points, and SPM co-registration performs the worst. And similarly, if we look at the FCNR, it tells a very similar story in that BBR still performs the best, and the three SPM realignment methods do very similarly. Again, the mask performs slightly better, but it's not very obvious in this data set, like from this graphs. Alright, so the next thing to think about was, since this works very well for 7T, should we bring this to 3T as well? So this is actually from another data set that I've acquired previously, and it has both 1.5 millimeter and 3 millimeter 3T data. And it's just, the three graphs are just three different sessions. There are slightly different manipulations, but they shouldn't affect the TSNR. And you can see that at 1.5 millimeter, the two methods basically generate identical results. And at 3 millimeter, the BBR actually performs worse than SPM. And this is kind of, I think this is kind of expected, especially at 3 millimeter, because your resolution at 3 meters is so low that you're don't actually have the boundary information to drive the realignment. And so this is kind of some videos of how it looks like. So if you compare the standard and BBR at 1.5 millimeter, they basically look identical. And whereas at 3 millimeter, you can see that the BBR actually has a bit more jittering of the brains. Alright. So in conclusion, what we've noticed is that while BBR is slightly more computationally expensive, it generates quite a bit of improvement at 70 sub-millimeter data. And what is interesting about this is that this improvement is an inherent property of using the boundaries as a cost function versus something like nearest neighbor or normalized mutual information. And this cannot be replicated by simply masking the brain or simply co-registering to a structural. And again, there's no apparent benefit for using this in 3T, where standard realignment seems to be sufficient, if not better. Right. So I'd like to thank Martha, Rick, and Johan for being my supervisors, and as well as some other people who have helped, Siri, Kat, and Chris. And yeah, thanks for your attention.